Welcome to Maths with EJD. Today, in this video, I'm solving a structured problem, two-part problem, right? And it's about metric spaces. The first one talks about this, define the following. Define the following. One, open set, open set. Two, closed set, closed set. Three, sphere. Okay, so let's deal with that first of all. So define open set, closed set, and then sphere. Or of course, since we know we are talking in the context of metric space, right? Now, the whole idea of metric is distance. The whole idea of metric is about distance between 2 points. So that's what metric is all about. So talking about the first one, which is open set, right? Open set. Um, we need to know that in a metric space, a set, a set is called open. A set is called open if for every point, if for every point in the set, if for every point in the set, there exists a small neighborhood, a small neighborhood, a small neighborhood, a small neighborhood around that point that is entirely, that is entirely, entirely contained, contained within the set, entirely contained within the set. So that is an open set. So a set is said to be open if for every point in the set, there exists a small neighborhood around that point that is entirely contained within the set. A very good example of an open set would be this. If we have this 1, 2, 3. Okay, or better still, let's just do this. We have 1, 5. So as an open set, right? What we are saying here is that, this kind of set, if we are talking about just the whole numbers alone, it doesn't have to be whole numbers alone, but let's assume that we are just focusing on the whole numbers. The integers. So if you're focusing on the integers, so this kind of bracket tells you that it's an open set, meaning that the values 1 and 5 are not included in the set. So the elements of this set are simply 2, 3, and 4. If we are considering integers, of course, we could actually be talking about things like 1.001 and so on and so forth. But if you focus on just the integers, right? So the elements of this open set will be 2, 3, 4, 2, 3, and 4. So in the case of this open set, 1 and 5 are not members. But talking about the fact that there exists a small neighborhood around that point, that we say in a metric space, a set is called open if for every point in the set. So it means that if 2, 3, and 4 are in this set. So if you take 2, for instance, and if you add 0.1 to 2, or you subtract 0.1, that's like you having 1.9 and then 2.1, right? So the small neighborhood, and a very good example of this small neighborhood around that point. So if we take 2 as our point and we take 0.1 as our small neighborhood. So what an open set is that even all these small neighborhood are also still totally contained within that set. And as you can see, right, this set should actually contain everything from like maybe 0.001, so to speak, anyhow you like it, up to say 4.99 something, right? So if you add this small neighborhood 0.1 or you subtract it, everything still lies within the set. That is what that is about, right? Okay. So let's move ahead and talk about a closed set. Two, a closed set. Closed set. Closed set. All right. So a set, a set is said to be closed, is said to be closed, is said to be closed if it contains, if it contains all its limit points, all its limit points. In the case of an open set, right, the limit points are excluded. 1 and 5 are the limit points here, but they are excluded in an open set. But in a closed set, the limit points are included. So a set is said to be closed. So a set is said to be closed if it contains all its limit points. So for instance, if, okay, we had 1, 5 there, right? So if you now have this, this symbol, this square bracket actually means that it is a closed set, meaning that the elements of the set include 1 and 5. One, so here you can, if you talk about just the integers, right? It means you have 1, 2, 3, 4, and 5. So you see 1 and 5 are included here. And that is exactly the idea of a closed set. A set is said to be closed if it contains all its limit points. So the limit points 1 and 5 are contained as members of the set, basically. So that's the idea of a closed set, straight to the point. Okay, so let's move on to the idea of a sphere. What is a sphere? Of course, a very good example of a sphere is a ball shape. It's like three-dimensional circle. And the one thing about a circle is that it has a radius. So we can say that a sphere of radius r, a sphere of radius r, centered at a point, centered at a point x, centered at a point x, is the set, of all points. It is the set of all points. It is the set of all points at a distance, distance r from x. So if I'm going to give, if I'm going to demonstrate that, right? So you have this point x as the center, right? And then you can have radius r in different directions, radius r, radius r, radius r, some three-dimensional stuff. Um, I'm trying to think of how I can do, okay, so you have that radius r, so that at the end of the day, you have something like this, you know, uh, nah, that's not coming out well. Okay, you have like a circle, you have radius r, all the way. But then it's three-dimensional. It's three-dimensional. Even onto the surface, you know, even onto the surface, you have radius r like that. So something like that. That's a very rough one, but I mean that's just the idea. So a sphere is basically a three-dimensional circle if you like to think about it in that way. So the idea is that from the center to any surface of the sphere, the distance is the same. It is that radius. So it is the set of all points, you can say, equidistance from x. And the value of that distance is actually r. So that takes care of the first part of the question, which is to define those concepts. So that being said, can we go to the second part of the question? Let's look at the second part of the question. It involves some more serious thing. Let's see what that looks like. Okay. So we have seen the A part of the question. Let's do the B part. So for the B part now, we say let x be equal to, okay, let x be equal to the set of all real numbers. And then you have P now to be defined on R by R. So like something two-dimensional, right? And which is mapped to a one-dimensional thing. So what this means that this takes two inputs and gives one output. That is basically what that means. So it takes on two elements from the real number system, from the real number system, and gives one output that is also a real number. So we are saying that P now is a metric. Let it be a metric. Like I said already, metric is simply a distance. So be a metric on R, that's on the real number line, defined for all. So this symbol means for all X and Y belonging to the real number, belonging to the real number by, so this is the definition now, that P of XY is a step function, which is 0. It is 0 if X is equal to Y, and it is 1 if X is not equal to Y. All right. So I think this is what is called a discrete metric space or something like that. So it means that this P now is a metric, all right? It's a distance. So P of XY means the distance between X and Y. And another way to write that is this. Oh, okay, well, I'll talk about all that later. Let me finish up the question. So far, let X be the real number system, and P, which maps R by R to R, is a metric on R defined for every X and Y belonging to the real number by P of XY equals, it is 0 if X is equal to Y, and it is 1 if X is not equal to Y. So then we have the following. We want to describe the open ball. Describe the open ball. So the first open ball we want to describe is B of 1 comma half. The second open ball we have to describe is B of 1 comma 1. The third open ball is B of 4 comma 3 over 2. And the fourth open ball is B of 1 over 4 comma 2. Then lastly, we have this. We want to show that P, which is a metric, right? We want to show that P as defined above, is a distance function. Is a distance function. The distance function, meaning that we want to show that P is actually a metric. That's what that is about. Okay, so let's go. So we want to describe these open balls based on this definition, right? So it means that, generally speaking, first of all, we need to be able to define what a ball is. Okay. So to take care of that, right? Let's start by defining in general terms what a ball is, an open ball for that matter. So an open ball centered, at a point, X with radius R, centered at a point X with radius R, can be expressed as BR of X, which is equal to the collection of all Y belonging to the real number system, such that P of XY is less than the radius R. So it's an open ball if it is less than R. But if it was less than or equal to R, that would be a closed ball, meaning that R is included. But open ball means it is less than R, so the distance is always less than R. That's what makes it an open ball. Now, for the sake of easy usage, right, I like to also write this as BR of X, which is equal to the collection of every possible Y you can get belonging to the real number system, such that the absolute value of X minus Y, that's the distance between X and Y, is always less than the radius. So that's the definition of an open ball. So once you know this definition, you can always use it to describe any kind of open ball you're told to describe. So with this definition, we can get cracking as we, begin to describe the open balls you have been told to describe. So let's go green. It's been a long time using green. So let's go. So first of all, we want to describe the open ball B1 comma half. B1 comma half. So this means this is the center X, and this is the radius. So that means that we can say this is B half, the radius, going by this, B radius X. So B half 1, that's the center. And of course, that will be equal to the collection of all y such all y belonging to the real number system such that the absolute value of x now is this one. So 1 minus y, is always less than the radius half. Always less than the radius half. So that's how you can do that. And one thing we need to understand is that whenever you have the absolute value of a less than b, it is the same thing as minus b less than a less than b. So that's extremely important to note. So if that is the case now, then we can bring this down and say that it is actually b half 1, or better still, we can maintain the original thing. We have already used this. So b1 half now is equal to the collection of all y belonging to real number, and that is minus half less than 1 minus y less than half itself. So going by this expression, right? So let's do some things. So we want to actually get the range of values for y that satisfies this. That's exactly our business here, to describe that ball. So of course we need y to stay alone. So we can subtract y from all the sides. So that means we have the collection of all y, the collection of all y in R such that we have minus half minus y less than 1 less than minus y less than half minus 1. Okay. So we have the collection of all y belonging to R such that we have minus 3 over 2 less than minus y less than minus half. Correct? Yeah. So now you see minus y is in the center and you want to get rid of minus. So you can multiply through by minus. So you have the collection of all y belonging to the real number system such that, and once you multiply through by minus, right, the the inequality sign will be reversed, because minus 3 over 2 is less than minus 1 over 2. But if you multiply through by minus 1, then half is going to be less than uh half is going to be less than 3 over 2. So if you multiply through by minus 1, and you have 3 over 2 greater than y greater than half. And you can rewrite that as y belonging to R such that half is less than y is less than 3 over 2. So the values of y that satisfy this ball, this ball 1 comma half, the ball with center 1 and radius r. So the values of y will have to be between half and 3 over 2. And that is one way to describe this thing. So there are other ways by which you can describe it. You can say what the ball contains and what it doesn't contain. But I feel, talking about the range of values of y that satisfies it, I think is also a good enough way to describe the ball. In fact, for me, that's about the most empirical way. Like, we follow a standard formula to do that. Okay, so we have described that first ball. Let's look at the second open ball we need to describe, and that is the second one, B1, 1, which is the same thing as B radius 1, center 1, basically. That is y belonging to all real numbers, such that you have the absolute value of x, which is 1. X is 1 here, minus y, less than 1. The radius is 1. So again, we go the whole hog and we say the collection of all y in R such that we have minus 1 less than 1 minus y less than 1, based on what we said the other time. And now we have all the collection of y belonging to R such that if you subtract minus 1 from all the sides, you get minus 2 less than minus y less than 0, subtracting 1. So if you multiply through by minus 1, right, you have y belonging to all R such that you have 2 greater than y greater than 0. And then it's the collection of all y belonging to R such that belonging to the real number system, right? So now this is 0 less than y less than 2. And that is it. So that is what you get. Of course, like here, right? Yeah, you can say that yeah, I mean, we can leave it there, right? We can actually leave it there, yeah, we can leave it that way. So that's the second one, right? And the third one is what we have to deal with next. So for the third one, we have 3, right? Which is b 4,3 over 2. That is b. The radius is 4. Sorry, the radius is 3 over 2, and the center is 4. This is x and this is r. Okay, so the radius is 3 over 2, and the center is 4. So again, you go collection of all y belonging to the real number system, such that the absolute value of x minus x, here x is 4, right? X is 4 minus y, and that is less than 3 over 2. So we go again, and we have the collection of all y belonging to R, such that minus 3 over 2 is less than 4 minus y, is less than 3 over 2. And then we have the collection of all y belonging to R, R real number, such that if you subtract 4 from both sides, that's like minus 3 over 2 minus 8 over 2, that's minus 11 over 2, less than minus y, less than 3 over 2 minus 8 over 2, that's minus 5 over 2, Multiply through by minus 1, you need the collection of all y belonging to the real number system, such that multiply through by minus 1 now, so you have 11 over 2 greater than y, greater than 5 over 2. Once you multiply by minus 1, the inequalities change, right? The inequalities change, like it's been changing since. So, and then you can now rewrite this as the collection of all y belonging to R, such that 5 over 2 is less than y, is less than 11 over 2. And that is what describes B for 3 over 2, B for 3 over 2. Just like here, this described B 1, 1, and so on and so forth. Okay, so we do the last one where we have B now, the fourth open ball. B of 1 over 4, comma 2, and that is B, the radius is 2, the center is 1 over 4, and that is a collection of all y belonging to the real number system, such that the absolute value of x is 1 over 4 minus y, is less than the radius, which is 2. The radius is 2. So we have the collection of all y belonging to the real number system, and we have minus 2 less than 1 over 4 minus y less than 2. Okay, and then we subtract 1 over 4 from all sides. So we have y in R such that minus 2 minus 1 over 4 is like, minus 2 is the same thing as 8 over 4. So we have minus 8 over 4 minus 1 over 4. That's minus 9 over 4, I believe. Yes, so minus 9 over 4. And then that is less than minus y, and that is less than 8 over 4 minus 1 over 4, that is 7 over 4. So we can multiply through by minus 1. So we have y in real number system. Multiply through by minus 1, you have 9 over 4 is greater than y, which is greater than minus 7 over 4. And that can be rewritten as a collection of all y belonging to R, such that minus 7 over 4 is less than y, is less than 9 over 4. And that is what describes the ball with center 1 over 4 and radius 2, basically. And that's how that has been. So we have the fifth thing to do. The fifth thing is to show. We want to show that P is a distance function, That is, P is a metric. We want to show that P is a distance function. So don't forget, P of x comma y is the same thing as 0 if x is equal to y. It's a step function. It is 0 if x is equal to y, and it is 1 if x is not equal to y. Okay, so that's what we have to show. All right, so now there are four properties. There are four properties of a distance function, so we need to verify them. We need to verify the four properties, the four properties of a distance function, of a distance function. Okay. So let's look at the properties. The first property is non-negativity property, non-negativity, non-negativity. Okay, and what does that say? It says that P of xy is always greater than or equal to 0 for all x and y belonging to the real number system. That's what the first law says. The first property. The second property is identity. It's called the identity of indiscernibles. Indiscernibles. Identity of indiscernibles. And what does that say? It simply says that P of xy is always 0 if and only if and only if x is equal to y. That is the identity of indiscernibles. Okay. And 3 now, we have symmetry. We have symmetry. Symmetry here says that P of xy is the same thing as P of yx for all. Okay, let me use the math notation for all x and y belonging to the real number system. Okay. And finally, number 4, we have triangle inequality. Triangle inequality. So triangle inequality is just like going straight to a place takes you less time than going to somewhere halfway and then going from that somewhere halfway to the place. That's the kind of idea this portrays, right? So triangle inequality simply tells us that P of x, comma z is always less than or equal to P of xy plus P of yz for all x, y, z belonging to the real number system. So those are the 4 properties of a distance function. So for us to show that, we need to be able to show that all these 4 rules hold for this expression, for this metric P that we've been given. So let's start. Again, as a way of reminder, we know that P of xy is equal to a step function 0 if x is equal to y, and 1 if x is not equal to y. So then we go for the first property of non-negativity. Non-negativity. So 1, we can say 1 to prove non-negativity. To prove non-negativity, what do we do? In that case, right, we just say, we already know that P of xy is greater than or equal to 0, is greater than or equal to 0 for all x, comma y, for x, comma y in R. So this is what we need to prove, right? So to prove non-negativity, so what do? We already know that for x equals y, right? From the function, for x equals y, P of xy is equal to 0. That's 0, right? Then, and we know also that for x not equal to y, P of xy is equal to 1. So if that is the case, then we can say that, so P of xy is always greater than or equal to 0. So if it is 1, it's greater than 0. If it is 0, then it is equal to 0. So this is the proof for non-negativity. Very intuitive. Okay. So let's go for the next proof. Number 2 now. We want to prove the identity, of indiscernibles. Indiscernibles. Okay? Prove the identity of indiscernibles. So, and this is it. P of x, comma y, P of x, comma y is equal to 0 if and only if, this is the short form for if and only if x is equal to y. So this is what we need to prove here. So, and how do we go? So if and only if means that you want to prove it both ways. So you start from the right and you go left. So if and only if, anytime you hear something like if and only if, so it means you start from here and you end here, and you also start from here and end here. You have to do the 2 sides. That's the only way you can show that you can actually prove an if and only if thing. So what do we do? So if we want to go from left to right, right? So we say if P of xy is equal to 0. Of course, you already know that P of xy means the absolute value of x minus y, because P of xy is a metric, is a distance function. And distance between 2 points is the absolute value of the difference between them. So the absolute value of x minus y equals 0. That's what that implies. And of course, you can as well write this as x minus y equals 0, you know. And then from there, that means x is equal to y. So you see now you have started from here and you ended up from P of x from P of xy equals 0. You have ended at x equals y. So the other part is you want to go from right to left, right? You want to go from right to left. So from right to left, you now say if x is equal to y. Okay, they're starting from the other side now. You want to end up where you the other on the right, on the left hand side. So if x is equal to y, you can say that x minus y is equal to 0. And then the absolute value of x minus y is still the absolute value of 0, which is simply 0. And the absolute value of x minus y equals 0 is simply the same thing as the metric, the p of x of y, which is still 0. So either way, so if you start from p of xy equals 0, you end at x equals y. If you start from x equals y, you end at p of x y equals 0. That is the identity of indiscernibles. So you can say, therefore, p of x comma y equals 0 if and only if x is equal to y. So that's the third thing you have to prove. Okay, so let's go to the third thing you have to prove. So number 3, you want to prove symmetry, to prove symmetry, or if you like, you can call it symmetricity. And what does that say? It simply means that P of xy is equal to P of yx. Okay, for all x and y belonging to the real number system. So you have all this like this. Okay, so that goes. And you can now say that. So, I mean, the simple thing I'm just going to do here is I'll do the definition. P of xy is equal to 0 if x is equal to y, and it is 1 if if x is not equal to y. So you see, this is simply the same thing as saying it is 0 if y is equal to x, if y comes first, and 1 if y is not equal to x. And if you can turn it over like this, then this is as good as having p of y comma x. So you start from p of x equals y and end at p of y and p of x comma y, and you end at p of y comma x. So in that case now you can say, therefore, p of xy is the same thing as p of yx for all x comma y belonging to the real number system. Okay, so we have proven the third one. So the fourth thing we have to prove, the fourth property we have to prove is this. So we want to prove the triangle inequality. We want to prove the triangle inequality. The triangle inequality. I want to prove the triangle inequality. So to prove the triangle inequality here, what do you do? Of course, triangle inequality means P of xz. That's too big. P of xz equals P of xz rather is less than or equal to P of xy plus P of yz. So it's more like you have a point x and you have a point z. So we are saying that going straight from x to z, is shorter or at worst this exactly the same as going first to a point y, then before going to a point z. So that is the triangle inequality. So we want to prove this. Now, proving this is not as straightforward as you would expect, because we have to look at different scenarios. So one of the scenarios we have to look at is this. The first scenario, should I call that letter A, or let me just say dash? So first condition, if x is equal to y is equal to z. So if all the points are the same, So that's one scenario. So if x is equal to y is equal to z, so it means that p of x comma z, we already know that. So if they are equal, right, we have 0. If they are different, we have 1. So if x is equal to 1, x is equal to z. So p of x z is going to be 0 because x is equal to z. And then p of xy is also going to be 0. And p of yz is also equal to 0 because they are all equal. So in that case now, we see that p of xz is equal to, I mean, yeah, in that case, it is equal because p of xz is 0 and it is equal to p of xy, which is also 0, plus p of yz, which is also 0, like that. So that's the first case. The second case is, okay, let me go. If x now, the second case, if x is equal to y, not equal to z. So x and y are the same, but they are different from z. So in that case now, we know that p of x is z, x and z are different. So if they are different, that will be 1, right? So x, z are different, but we have p of x, y, p of x, y, that will be p of xy, because x and y are the same, that is 0. Then we have p of yz, because y and z are different, that will be 1. So again, we have p of xz equals, in this case now, 0 plus 1 is 1. So this is 1. So p of xz equals p of xy plus p of yz. So that means this is 1, and that is equal to 0 plus 1. Here you had 0 equals 0 plus 0. So you see p of xz is 1, p of xy is 0, p of yz is 1. So 0 plus 1 is 1. So they are equal in this case. Okay, so can we take the third possibility? So the first case, we looked at x, y, z all the same. Second one, we have x and y equal, but z is different. So what if we have x not equal to y, but y is z? Okay, that's another situation we can consider. So in this case, p of x is z, because x and z are different, the metric is 1, the distance is 1. What if we have p of x, y? P of x and y are different here, so we get 1 again because x and y are different. What if we have p of y, z? Y and z are the same, so we get 0 there. So again, we see that we can say therefore p of x, z is equal to p of x, y plus p of y, z. Okay? Because p of x is 1, and that is equal to p of xy is 1 because x and y are different. And then p of yz, that is 0. So 1 plus 0 is also 1. Okay? So the last possibility we want to check is if x is not equal to y, is not equal to z. Nothing is the same. So here we have p of xz to be 1 because everything is different. P of xy is also 1, and P of yz is 1, all the way 1, 1, 1. So here now we have therefore P of xz here, P of xz is 1, and then it's here now it's not equal, it's less. So P of x, which is 1, is less than P of xy, which is 1, plus P of yz, which is also 1. You see? So 1 is less than 1 plus 1, as you can see. So we have 3 cases of equality, and we have 1 case of less than. So putting everything together, right, we can now say, therefore, P of xz is less than or equal to P of xy plus P of yz, plus P of yz, as expected, for all x, y, z belonging to the real number system. So that is all we have there. And that brings us to the end of the question. It's been a very lengthy one. I hope you can follow through and get it. The concepts are very easy, and you just need to know how to go about it. So if you have not subscribed to this channel, be sure to do that. And of course, hit the notification bell so that you can always get notified whenever I release a new video. Always like, comment, and share. And I'll see you in the next video. Thank you.